Riemann sums and the definite integral. When we started this unit, we discovered that the integral geometric interpretation was the area between the function curve and the x-axis when we were working with a single input variable and single output variable. When we had functions with concavity, we also came across situations where the shapes that were produced that we needed to find the area for were not polygons, and they were not shapes that we had area formulas for. So what we did was utilize approximation methods through calculating the areas of rectangles and trapezoids to get an approximation for what the area would be. And we also discovered the more rectangles we used, or the more trapezoids we used, the better the approximation was. The act of approximating the value of the integral through the finite sum is what a Riemann sum is. So I'll repeat that one more time. A Riemann sum is the approximation of the value of an integral through a finite sum. The finite sum in our situation was the act of adding together the areas for the rectangles or the trapezoids. So you'll see here that I have a function drawn in blue, and it ranges along our interval from a to b. I have already divided up the interval from a to b into these subintervals labeled in green below, ranging from x sub 0 to x sub n, where n is the number of subintervals. We had various rectangular approximation methods, but let's just look at LRAM and RRAM. For an LRAM, what we did was add together the areas of the rectangles where the heights were produced through the function evaluation at the left endpoint of each subinterval. So if I were to do an LRAM on the situation that I have drawn above, we would be doing f of x sub 0 to get the output, and that would represent the height of my first rectangle on the first subinterval, and the length of that first subinterval would be x sub 1 minus x sub 0. And I would add it to f of x sub 1, x sub 2 minus x sub 1, being the output on the left endpoint of the second subinterval, and the difference between the endpoints of the second subinterval to find that length. And we could continue this process all the way up until the last subinterval. Now you could imagine when we have multiple rectangles to calculate, this is a pretty long expression to write. We can condense this into a much neater formation, and that will introduce some new notation that we're going to utilize to then come up with the definite integral. But before we do that, let's jump over to what the RRAM would be. So we'll stick with these two. The RRAM, we're now using the right endpoint to get the function output and therefore the height. So we have these long strings of the sum of multiple rectangles. So how do we condense this down? For the LRAM, what we're going to do is say this new sigma notation stands for sum. We are going to sum together the area of a rectangle multiple times. The area of the rectangle is going to be x, and we're going to put k. And the reason I'm going to put a variable there is because you'll notice in our string of terms that are being added together, the subscript for the x value that calculates the height is changing. So if it's changing, let's put a variable for it. Now, the difference between the endpoints of the subinterval could vary. We've seen that we could have different base lengths for our rectangles to get an approximation. And that could theoretically get us a better approximation. But as soon as we enter the idea of using an infinite number of rectangles, or as the number of rectangles approaches infinity, which we'll get to, we're going to have equal length subintervals. But for now, because the subinterval length could theoretically be different, let's just call the length of the subinterval delta x for the change in x. Now we're adding together the height base, so this represents in full the area of a rectangle. So we're going to continually add that. That's what that sigma notation is telling us. Now what we want to add to this is at the bottom of the sigma letter, you're going to put where you start. And that k thing is the thing that's changing. And with an LRAM, we want to start at 0. And you'll see to go all the way to the n, the very last one, we go up to n minus 1. And let's just make a note where n equals the number of subintervals or rectangles. So that's the summation notation for an LRAM. For an RRAM, the only thing we change is where we start and where we end. K is going to start at 1 and go up to n. This is notation for the Riemann sum. When adding together rectangles to approximate the value of the integral. So the notation I have written here is our notation for Riemann sum. So let's say the first one is a left Riemann sum. And the second one is a right Riemann sum. So now that we have this new notation down, so again, that sigma just means add together the areas of rectangles when k goes from 0 to n minus 1. So that summation notation, the thing on the bottom is where you begin and where the summation subscript ends. Now let's just look at the right Riemann sum. And let's say that we want the length of the subintervals to be the same. So delta x is now going to be the length of the interval divided by the number of rectangles we want. Okay. As soon as the number of rectangles approaches infinity, so the limit as the number of rectangles approaches infinity, we have just produced an exact way to calculate the area between the function curve and the x-axis. And we now introduce this new notation, which is the integral from a to b of f of x dx. So the integral from a to b, f of x dx, is the limit as the number of rectangles approaches infinity of the Riemann sum that is used to approximate the area between the curve and the x-axis. So let's break this thing down into multiple pieces so we understand what this whole thing is saying. This first thing, the limit as n approaches infinity. What this is doing for you is you're doing the number of rectangles approaches infinity. Number of rectangles we're using. This here, this notation, is the Riemann sum. We already know that this is our height calculation. and this is going to be our base, but the way it's written here is of equal length. Right? So we're taking the full length of the interval and dividing it by the number of rectangles we want to use. This last part is the notation for the definite integral. And let's break down the pieces of the definite integral. This a value is the lower limit, or the starting point of the interval. The upper limit. F of x, so this notation inside here, this is your integrand. And this is the differential. Now, this x value here, so it could be dx, it could be dy, it could be dz, whatever variable you're dealing with, what you want to recognize is this is your variable of integration. So that is what you are integrating with respect to. Much like when we have derivatives and we have dy dx, that differential on the bottom is telling you to differentiate with respect to x. But if I had dy dz, we would be differentiating with respect to z. So when I look at my integral and I see that differential at the end, the variable associated with it is telling you what to integrate with respect to. Now you'll notice some similarities within the integral in the Riemann sum, because we know the integral now geometrically represents the exact area. Between curve and x-axis. And what we should note is that the area, it's actually the net area. And we'll take a look at that in another video, but it's going to be the net area. So meaning if it's above the x-axis, assuming you're working left to right, the area is positive. But if you're below the x-axis, the area is negative. And that's what we're going to jump into in the next video when we're talking about properties of definite integrals. But we just want to introduce notation in this video and what this thing represents, where it comes from, what the ideas behind it are, and some vocabulary. So we have now notation for a definite integral, what it means geometrically, where it comes from in relation to our Riemann sums, and as the number of rectangles we use to approximate area approaches infinity, we end up getting an exact area. And that exact area is now represented through the integral notation. So know that the integral geometrically represents the net area between the function curve and the x-axis along the interval from a to b. And real quick to end it, you'll notice in the Riemann sum, we had our height times our base. You can think of this f of x as the height, and this dx, the difference between the x's, think of it like that, as the base. So height times base, you are summing this elongated s. You can think of like a sum from a to b of height, base. So we're summing together rectangles. So just pretty similar parallels drawn here from the Riemann sum to the actual notation for the definite integral. So that's where we will conclude the video, and in the next video we'll jump into the properties of the definite integral and why we have net area as opposed to total area.